Hi, thanks so much for having me on this panel. It's a pleasure to be among such diverse and talented colleagues, and thanks to Patrick and Claudia for inviting me. I'm a PhD candidate at the University of Waterloo, and I'm going to be presenting one of our research projects that I've been working on over the past year with Intuitive and the past couple of years with the Energy Council of Canada and Diamond Schmidt Architects. I want to give a big shout out to Patrick and the rest of our team, including Tristan, for helping on this research. I'm going to start talking about multifamily housing. That's where we started in our research because of the big problem that we have right now with energy, the energy that they consume, and also they're a big factor in affordable housing. So we have 3,000 towers that were built in a period of time that has now expired in terms of useful lifespans, and we need to address them very quickly. There's a lot of money being invested in these towers in a lot of ways to try to retrofit them. We're seeing a gap in feasibility studies of what to do with these buildings and how efficiently we can address them. Just to give you an idea of the market we're dealing with, so 3.9 million units need to be retrofitted by 2050 in Canada. So that gives us a total market of 1.2 billion just for the feasibility cost, the feasibility analysis cost prior to design. So it's a big problem. Where we come in is we try to create a tool that tries to optimize and inform the client to be able to make better decisions regarding their towers. I'm going to go through one pilot application. The Ken Sobel Tower is currently under construction in Hamilton. It is the first passive house retrofit tower in all of Canada. And in this study, we looked at alternatives of what could have been if we took a more expansive approach. So from all of the identified residential adaptation strategies, we picked out two, so recladding and extending. And we tried to optimize based on energy use, daylighting, life cycle carbon emissions, so global warming potential, and life cycle costs. As a first step, we took the existing building. We defined parameters and grids, and I'm sure we're going to hear more about it with element 5 and how modular construction works. But defining those parameters for modular construction is extremely important, especially when you're dealing with existing buildings. We defined patterns for growth. So where can this building actually grow? How does it make sense with the spatial layouts? And in what direction does it make sense to grow? After we had the module set, the volumetric modules, then we started looking at panels. So we set out multiple scenarios and picked out what panels need to go where, and we came up with a range of 25 set panels with different widths and lengths. In the next step, we started looking at possibilities of separate unit growth. So with one extension, you're going to have a larger unit, but then when you start to grow large enough, then you could divide up the units and generate extra revenue. I'll get into that later. In the next step, as the algorithm starts to generate design options, then we start parsing through those and eliminate the ones that further not meet our guidelines for design. An example of what that looks like. So with a simple extension, you're increasing the unit, which is great in a lot of cases. The clients that we've talked to, they're examples where a family of 10 is living in a 2-bedroom unit. So from a social sustainability point of view, it's very important to be able to extend some of those units. But it's also important for these buildings to start generating extra revenue so they can have sustainable paybacks. So keeping the same unit but extending to it is the ultimate goal. The next step after generating the design options, we solved for adjacencies and were able to assign materials. So floor assemblies, wall assemblies, and roof assemblies so that we could calculate the energy use and daylighting for each of those permutations. And the life cycle analysis and life cycle costing is also based on those material calculations. We also took into account the structural complexity of these modules. We defined a workflow A lot of this work was developed by my colleague at Waterloo, Chris Rauch. And so we were able to give a score to each of these modules and then factor that into our lifecycle costing and performance. So we ran the model for 2 weeks. We ended up with 600 permutations. Each took about half an hour. And right now here you could see the range of number of module extensions, daylighting, energy use, embodied carbon, and so on. From this interactive tool, we could start to filter out our limitations. For example, 40% and up is the acceptable daylighting range, and so on. From this graph on the right, we're showing life cycle analysis, so global warming potential and life cycle costing. And I'm just showing a chunk of this data to show you that within the same energy use and for the same amount of global warming potential, we could have a range of different design options that vary by cost. So that can start to help a lot of clients gain perspective of what they can do with their money. And then the last step, when we map lifecycle costing versus structural complexity score, which is a proxy for the design complexity, we could start to pick out the proto-optimal design solutions that look something like this. So the frontiers are here as an example, and the secondary options are here. This is what our results ended up looking like, 600 of these. So jumping kind of into the future work, we're working towards developing an interface that can streamline the whole process and make this tool easier to use. Right now, it's a whole bunch of different components. And the last thing that needs to be added to all of this is a financial analysis. As an example, what I spoke about earlier, developing new units, extra units, and that revenue can help pay back for this project. So in this example, we were able to generate 45 new units, 2 extra unit types. So right now there's a total of 4 with an 8-year payback, an internal rate of return of 8%, which is pretty good. So in the next 6 months, we're looking for more pilot projects, either new buildings or additions, adaptations like I showed you here. And hopefully in the next 2 years, when we have enough data, we could start to develop predictive models that can even make this process faster. Thank you very much, and I look forward to the discussion. Thank you.